On June 22nd, 2026, a paper landed in the journal Nature that quietly rewrote what we thought we knew about a visitor now leaving our solar system forever. It wasn't a planet, it wasn't a star, it was a comet barely a few kilometers wide, and according to the James Webb Space Telescope, it might be older than our sun itself. Not older by a little, twice as old. To understand how a single rock, tumbling through space, forced some of the most careful scientists on Earth to reconsider the timeline of our own galaxy, you have to go back to the night someone first noticed it wasn't behaving like anything we had ever tracked before. On July 1st, 2025, a survey telescope in Chile, part of a network called ATLAS, the Asteroid Terrestrial Impact Last Alert System, picked up a faint point of light moving against the background stars. ATLAS exists for exactly this purpose. Its job is to scan the sky night after night, looking for anything that might be heading toward Earth. Most nights it finds nothing unusual. This was not most nights. The object was moving too fast. Not fast in a way that suggested danger, but fast in a way that made no sense for anything born in our solar system. Objects that belong here, asteroids, comets, even long-period visitors from the outer edges of the sun's gravity, all move in curves that eventually bring them back. This one didn't curve. It moved in almost a straight line, tearing through space at over 60 kilometers per second, on a path that would take it in, around the sun, and back out into the galaxy, never to return. There is only one explanation for a trajectory like that. It didn't come from our solar system at all. It came from somewhere else, another star, another region of the galaxy entirely, and it had been drifting through interstellar space for who knows how long before it happened to cross paths with us. Astronomers gave it a name, 3IATLAS. The 3I means it is only the third interstellar object ever confirmed passing through our solar system, following an earlier visitor called Oumuamua in 2017 and a second one called Borisov in 2019. 3 objects in less than a decade, after decades of searching that found nothing. That alone should tell you something about how much has changed in what we're able to see. Before ATLAS confirmed the discovery, astronomers went back through older archived images taken earlier that year, searching for any faint trace of the object that might have gone unnoticed at the time. They found it. Images captured weeks before the official discovery date already showed a faint smudge of light sitting exactly where the object's calculated path predicted it should be, meaning it had been recorded, unrecognized, and data already sitting untouched until someone finally knew what pattern to search for. That's often how discoveries like this actually work. The object doesn't announce itself. It has to be found twice, once by accident and once on purpose. Once its orbit was confirmed, researchers calculated something remarkable, just how fast this thing was actually moving relative to everything else nearby. Near its closest approach to the sun, 3IATLAS was traveling at roughly 68 kilometers per second. Even far from the sun's pull, out in the emptiness of interstellar space, it retains a velocity of around 58 kilometers per second. Its so-called hyperbolic excess speed, the pace it will keep coasting at forever, long after the sun's gravity lost any meaningful grip on it. Nothing born inside our solar system moves like that. Every planet, every asteroid, every ordinary comet we've ever tracked is gravitationally bound to the sun, looping on some closed path, however long that path might be. 3IATLAS was never bound to anything here. It was simply passing through on a line that started somewhere among the stars and would end somewhere among the stars again, with our solar system as nothing more than a brief, coincidental waypoint along the way. But 3IATLAS was different from both of the interstellar visitors that came before it, and those differences are exactly what pulled NASA's most advanced space telescope into the chase. Oumuamua, the first confirmed interstellar object, was strange in its own right. It was elongated, tumbling end over end as it moved, and showed no visible tail, no glowing halo of gas, the kind of signature you'd expect from a comet warmed by the sun. Astronomers only had a few weeks to study it before it became too faint to track, and in that short window, they never managed to fully agree on what it actually was. Was it a rocky asteroid, unusually shaped by some process we didn't yet understand, or something else entirely? Its lack of a normal cometary appearance, combined with a slight, unexplained acceleration as it left the solar system, sparked years of debate, including a controversial suggestion from at least one prominent scientist, the same one who would later turn his attention to 3IATLAS, that it might not be a natural object at all. Borisov, the second visitor, behaved more like a familiar comet. It had a visible tail, a coma of gas and dust, chemistry that mostly matched what astronomers already knew from comets born in our own solar system. 3IATLAS arrived carrying a coma too, evidence of ice turning directly into gas as sunlight warmed it. But when scientists actually measured what that gas was made of, the numbers didn't match anything they had cataloged before. That's when the world's most powerful space telescopes started turning toward it, one after another. On July 21st, 2025, the Hubble Space Telescope captured its first clear image of the object, while it was still nearly 277 million miles from Earth. What Hubble saw was a small, solid nucleus wrapped in a teardrop-shaped cocoon of dust, glowing faintly as it began to warm. Because the comet was moving along a hyperbolic path rather than a stable orbit, Hubble had to track it directly during the exposure, which meant the background stars streaked into thin lines in the finished image, while the comet itself stayed sharp and still, the reverse of almost every astrophotograph you've ever seen. Based on that early imaging and later follow-up observations, astronomers narrowed the size of the nucleus down considerably. The upper limit on its diameter came out to roughly 3.5 miles, or 5.5 kilometers, though later estimates suggested it could be far smaller, possibly as little as 1,400 feet, under half a kilometer across. Either way, it was small enough that it posed absolutely no danger of ever reaching Earth, but large enough and moving fast enough to be unmistakably real and unmistakably worth the attention of every major telescope that could be turned toward it. Then, on August 6, 2025, the James Webb Space Telescope pointed its instruments at 3IATLAS for the first time. Webb didn't take a picture in the traditional sense. It used an instrument called the Near Infrared Spectrograph, or NIR spec, which doesn't just see light, it breaks that light apart. The same way a prism splits sunlight into a rainbow, revealing the exact chemical fingerprints hidden inside it. Every gas leaves its own signature in that spectrum. Water leaves one mark. Carbon dioxide leaves another. Webb was built to read those marks with a level of precision no previous telescope could manage. And what Webb found surprised the researchers analyzing the data. The coma surrounding 3IATLAS wasn't dominated by water vapor, the way most comets in our solar system are. It was dominated by carbon dioxide. Alongside the carbon dioxide, Webb detected water, carbon monoxide, water ice, and something unexpected for a natural comet, a foul-smelling gas called carbonyl sulfide, the same compound responsible for the rotten egg odor associated with some volcanic and industrial processes here on Earth. A carbon dioxide-heavy coma isn't unheard of, but for a comet observed this far from the Sun, it was unusual enough to raise questions immediately. Comets in our own solar system typically start releasing large amounts of water vapor once they're close enough to feel meaningful solar heat. But 3IATLAS was still relatively far out when Webb took this reading, in a temperature zone where water ice usually stays locked solid, while more volatile compounds like carbon dioxide can already begin escaping. That imbalance told researchers something important about how the comet's interior might be layered, and it raised a deeper question that wouldn't be answered for months. Why would an object built in some other solar system entirely be releasing so much carbon dioxide relative to water, this far from a star that isn't even its own? Researchers didn't have a definitive answer yet, but they had a theory worth testing, and testing it meant waiting. 3IATLAS was still heading inward, toward its closest approach to the Sun. Scientists needed to watch what happened when the heat became more intense, when more of the object's buried ice would finally have enough energy to turn to gas. So they waited, tracking the comet with telescope after telescope. NASA's Mars Reconnaissance Orbiter photographed it in October as the object passed near Mars on its way toward the inner solar system. The European Space Agency's JWST spacecraft, on its way to Jupiter's icy moons, captured images of it too on November 6th, thousands of miles from Earth. A machine built for one mission accidentally becoming a witness to another. The recently launched SphereX Observatory joined in as well, contributing its own infrared measurements of the dust and organic molecules drifting off the object's surface. On October 29, 2025, 3IATLAS reached perihelion, its closest approach to the Sun, passing at a distance of roughly 1 1/3 times the distance between Earth and the Sun. For a few tense weeks, the comet was positioned almost directly behind the Sun from Earth's point of view, effectively hidden from most ground-based and orbital observation. That blackout period mattered, because comets don't always survive close solar encounters intact. The heat and radiation near perihelion can fracture a nucleus, or in rare cases, break it apart entirely. Astronomers had no way of knowing during those weeks of silence whether 3IATLAS would emerge on the other side in one piece, or whether the only interstellar visitor observed with this level of detail would simply disintegrate before anyone got a second look. It survived. And as it began moving away in December 2025, freshly warmed and actively venting gas, scientists turned Webb toward it again, for what would become its most important observation yet. This time, Webb collected something it had never captured from an interstellar object before, a mid-infrared chemical fingerprint. Where the earlier August observation had focused on one narrow slice of the light coming from the comet, this new data captured a broader, more detailed picture, including the detection of methane, another gas not typically associated with the kind of chemistry astronomers expected from an object born so far from any familiar star system. But the detail that mattered most wasn't just which gases were present. It was the ratios between them, specifically the ratio between two forms of hydrogen, ordinary hydrogen, and a heavier version called deuterium, sometimes referred to as heavy hydrogen. That ratio matters because it acts like a kind of chemical clock. The proportion of deuterium to ordinary hydrogen locked inside a comet's ice depends heavily on the temperature and conditions of the environment where that ice originally formed, billions of years ago, around whatever star the object came from. Comets in our own solar system have a fairly consistent deuterium signature, one that lines up with conditions in the early solar nebula, the swirling disk of gas and dust that eventually became the sun and planets. 3IATLAS did not match that signature. According to the research led by astrochemist Martin Cordner of NASA's Goddard Space Flight Center and published in Nature on June 22, 2026, the carbon and deuterium ratios measured in 3IATLAS pointed toward an origin environment unlike anything found in our own solar system's history. Working backward from that chemistry, using models of how these ratios change depending on the age and temperature of the environment where ice first forms, the team estimated that 3IATLAS likely formed somewhere between 10 and 12 billion years ago. Our solar system, by comparison, is about 4.5 billion years old. That means, if the estimate holds up, 3IATLAS isn't just a visitor from another star. It's a visitor from a completely different era of the galaxy's history, formed when the universe itself was less than half its current age, drifting through interstellar space for longer than our sun has existed, before it happened to cross paths with a small blue planet that had, only recently in cosmic terms, developed the technology to notice it at all. Let that sit for a moment. Every atom inside that comet's nucleus has been traveling, essentially undisturbed, since before our sun ignited. It has passed through regions of the galaxy we will never see up close, shaped by radiation and starlight from systems that may no longer even exist. And for a few months in 2025, out of the roughly 10 billion years it has existed, it happened to swing close enough for our instruments to finally take a look. That kind of discovery is exactly the sort of finding that should have dominated headlines on its own merits. Instead, it collided with a very different and far more sensational storyline that had already been building since the comet was first discovered. Almost as soon as 3IATLAS was spotted, one voice in particular began pushing a very different explanation for its strange behavior. Avi Loeb, an astrophysicist at Harvard, had already built a public reputation around a controversial claim years earlier, that Oumuamua, the first interstellar object discovered back in 2017, might not have been a natural comet or asteroid at all, but possibly a piece of alien technology. When 3IATLAS appeared, Loeb applied a similar lens to it, publishing analyses that questioned whether the object's size, its trajectory, and certain features observed in its coma might point toward something artificial rather than a naturally forming comet. Over the following months, Loeb's speculation escalated. Early on, he pointed to what he called anomalies, features of the object's size, brightness, and trajectory that he argued fit poorly with a simple cometary explanation, and used those anomalies to argue that ruling out an artificial origin required more caution than most astronomers were giving it. He proposed the object might function as some kind of technological probe. In one widely shared piece, published under a title that played on the object's own designation, he floated the possibility that its behavior could even suggest an intelligence responding to what it observed of humanity as it passed through. He calculated a measurable non-gravitational acceleration in the comet's path, a real observed effect where an object's trajectory shifts slightly due to forces beyond gravity alone, and argued the specific pattern was unusual enough to warrant considering an artificial explanation. In one estimate, he assigned roughly a 40% probability to the idea that 3IATLAS could be a spacecraft rather than a natural object, a number he described carefully, but one that traveled through media coverage far less carefully than he framed it. He pointed to a glow observed in a Hubble image from July 21st and suggested it was inconsistent with simple reflected sunlight or the presence of rare interstellar material, ruling those explanations out in his own analysis and returning again to the idea that the object could be releasing energy of its own. By the time 3IATLAS approached its closest pass, some of this speculation had escalated even further in public discussion, with the idea occasionally framed not just as a possible probe, but as something potentially unhappy with what it observed of human activity on its way through, or as what Loeb described as a possible black swan event, a term usually reserved for catastrophic, high-impact surprises nobody sees coming. None of this framing was ever supported by direct evidence. It remained speculation built on real but ordinary data, interpreted through a lens that assumed the more extraordinary explanation before ruling out the simpler one. It's important to be precise here about what was fact and what was interpretation. The non-gravitational acceleration itself was real and measured. Comets experience this regularly. It happens when gas venting unevenly off a comet's surface acts like a tiny, uncontrolled thruster, nudging the object's path slightly away from a pure gravitational orbit. Nearly every active comet ever tracked shows some version of this effect. What was not established was Loeb's interpretation that this particular pattern of acceleration required an artificial explanation, rather than the same natural outgassing process seen in comets throughout recorded astronomical history. The scientific response was, for the most part, direct and consistent. Observational evidence gathered by Hubble, by the Vera-C, Rubin Observatory, and by Webb itself all pointed toward classical cometary behavior. Outgassing, water ice, a dust coma with polarization properties consistent with countless comets studied before it. NASA and the broader astronomical community classified 3IATLAS as exactly what its early data suggested: an ancient, naturally forming comet, unusual in its chemistry, but not unprecedented in its physics. Even the Pentagon's office responsible for investigating unidentified phenomena stated it had found no evidence connecting the object to extraterrestrial technology. Some researchers went even further, actively searching for any sign that might support the artificial hypothesis, just to rule it out properly, rather than simply dismissing it outright. Radio astronomers scanned the object across a wide range of narrowband frequencies, the kind of tightly focused signal that, if detected, would be almost impossible to explain as a natural phenomenon and would represent close to a smoking gun for genuine technology. They found nothing, no transmissions, no structured signal of any kind, just the quiet, chemical breath of a comet, outgassing as it warmed in sunlight, exactly as billions of comets have done before it, and exactly as the mainstream data had suggested from the very beginning. Even Loeb's own Galileo project, the research initiative he founded specifically to search for possible extraterrestrial technology using dedicated cameras and sensors, turned its instruments toward the question without producing anything that confirmed the hypothesis. None of that stopped the public conversation from taking on a life of its own. Researchers studying online discourse around 3IATLAS found that a striking share of social media posts about the object invoked the possibility of aliens, with spikes in that conversation tracking almost perfectly with Loeb's media appearances and with major milestones, like the comet's closest approach to the Sun. It became a case study in how quickly scientific uncertainty about something genuinely unusual can be reframed into something far more dramatic than the evidence supports. To be fair to the questions being asked, if not always to the conclusions drawn from them, the impulse to check is not unreasonable. When something as strange as an object twice the age of our Sun turns up unannounced in our solar system, ruling out every possibility, however unlikely, is part of doing science, honestly. The problem was never that scientists asked the question. The problem was the gap between a hypothesis worth testing and a hypothesis being presented, in headlines and interviews, as something close to confirmed. What actually was confirmed by the time 3IATLAS faded from view in mid-2026 was arguably more remarkable than the speculation surrounding it, even if it required no aliens at all. Here's what we know, based on the combined observations from Hubble, Webb, SphereX, and ground-based observatories around the world, and what remains genuinely uncertain. We know 3IATLAS is only the third confirmed interstellar object ever detected passing through our solar system, a rate of discovery that has accelerated dramatically as survey telescopes like ATLAS and upcoming instruments like the Vera-C, Rubin Observatory, have become sensitive enough to catch objects that would have gone completely unnoticed even a decade earlier. We know its nucleus is small, with estimates ranging from under half a kilometer to a little over 5.5 kilometers across, depending on which observation and which modeling assumptions are used, but in any case, far too small to pose any threat to Earth. Its closest approach never brought it anywhere near our planet. We know its trajectory is hyperbolic and retrograde, meaning it doesn't orbit the Sun the way planets and most comets do, and it's moving in the opposite direction of most objects in our solar system. Further evidence that it was simply passing through on a path shaped entirely by wherever it began its journey, star systems and galactic structures far beyond anything we've directly observed. We know its coma is unusually rich in carbon dioxide compared to water, an unusual chemical ratio that stood out from the moment Webb first analyzed it in August 2025. And we know from the deuterium and carbon isotope ratios measured during Webb's follow-up observations in December of that year that the ice locked inside this comet appears to have formed under conditions dramatically different from anything in our own solar system's history, conditions consistent with an age of 10 to 12 billion years, more than twice the age of our Sun. We know it passed relatively close to Mars' orbit on its way through the inner solar system, close enough that scientists briefly discussed whether orbiters already stationed around Mars might catch a clearer view than anything possible from Earth. And NASA's Mars Reconnaissance Orbiter did exactly that, adding its own images to the growing archive of observations. What we don't know, and what may never be fully settled, is exactly which star system 3IATLAS originally came from, or what specific environment shaped its unusual chemistry so many billions of years ago. Objects like this arrive with no return address. Once they leave, tracing their path backward across billions of years and unimaginable distances becomes close to impossible with current technology. Even with a well-measured trajectory, the comet's path has been reshaped countless times over billions of years by the gravity of stars it passed near on its long journey, meaning any attempt to trace it back to a single point of origin quickly dissolves into uncertainty far beyond what our instruments or our mathematics can currently resolve. By the time you're hearing this, 3IATLAS has already continued past the orbit of Jupiter, accelerating away from the Sun, retreating into the same interstellar darkness it emerged from roughly a year earlier. It will not come back. There's no return trip built into a hyperbolic trajectory like this one. Whatever instruments manage to catch a final glimpse of it as it fades past the edge of our solar system's reach will likely be the last ones to ever see it at all, which leaves us with a strange kind of privilege and a strange kind of loss, arriving at exactly the same moment. For a period of less than 2 years, humanity had the tools and the timing to notice an object that had been drifting through the galaxy since before our sun existed, to break apart its faint light with a space telescope, and to read, in the chemistry hidden inside a small ball of ancient ice, a message about conditions from a corner of the universe we will likely never visit or identify. It didn't need to be an alien probe to be extraordinary. It needed only to be exactly what the data showed it to be, a fragment of the deep past, older than our star, passing close enough, just once, for us to finally understand a little more about how much of the galaxy's history has been drifting past us all along, unnoticed until instruments powerful enough to see it finally came online. Consider what that actually means for how we think about our own galaxy. If a single comet, formed 10 to 12 billion years ago around some long-vanished star, can drift for that many billions of years and still happen to cross paths with our tiny corner of the Milky Way, then interstellar space almost certainly contains an enormous, largely invisible population of similar objects, fragments of countless other planetary systems, most of which we will never detect, quietly tracing their own hyperbolic paths through the galaxy on timescales that dwarf human history entirely. 3IATLAS wasn't a rare fluke created just for us to find. It was simply the third one we happened to be looking in the right direction to catch, out of what may be an uncountable number that have already passed through our solar system unnoticed, long before Atlas or Hubble or Webb ever existed to see them. The next interstellar visitor is likely already out there too, somewhere between the stars, following its own hyperbolic path toward a future encounter nobody has predicted yet. With observatories like the VERC, Rubin Observatory now coming fully online, built specifically to scan the entire visible sky repeatedly and catch faint, fast-moving objects that older surveys would have missed entirely, astronomers expect these detections to happen far more often than the decades of near silence that preceded Oumuamua's discovery in 2017 ever suggested. Some estimates now propose that once Rubin reaches full operational capacity, astronomers could identify a new interstellar object every year, or even more frequently, transforming what were once-in-a-decade events into a regular, almost routine part of how we watch the sky. Which means the real question isn't whether we'll see something like this again. It's what we'll be ready to learn the next time something older than our sun quietly drifts into view, and how long it will take us, this time, to separate what the evidence actually shows from the story we most want it to tell.